All right, so far we've started to look at a few elementary integration techniques, and basically what we have is guessing and checking. That's about it right now. What I want to show you right now is how to use what's called the change of variable method for integrating, and it's really a lot like U-substitution for integrals. Remember that if we were going to integrate the square root of 2x minus 1, what we would do is recognize that this 2x minus 1 here is underneath the square root. So we treat it as a square root function, and we would guess that, square root of 2x minus 1 is 2x minus 1 to the 1/2 power. So I would guess that we would raise the power by 1. So bring that to the 3/2. And then divide by that 3/2, so we get a coefficient of 2/3. Of course, that's just a guess, so we would have to check that. So we would take the derivative of 2/3 times 2x minus 1 to the 3/2 power, and that would be that we'd bring the power down. 2/3 times 3/2 is 1. 2x minus 1, we decrease the power by 1, so we'd have 1/2. But this is a chain rule, so we have to multiply by what's in the derivative of what's inside. So the derivative of 2x minus 1 is just 2. Then we compare what our derivative is to our original integral, and we see, are they the same? And they're close, but they're not exactly the same. In fact, when we took that derivative, the dy dx, we ended up with something that was 2 times as big. So in order to make that adjustment, what we're going to do is go back and we would have to multiply that by 1/2. So I'm going to have to take my guess and multiply that by 1/2 as well. Okay. So we would end up with an answer that is 1/3 times 2x minus 1 to the 3/2. And if you were to check that, d dx of the 1/3 of 2x minus 1 to the 3/2, we'd bring the power down, and so we'd have 1/2 times 2x minus 1 to the 1/2 multiplied by the derivative of the inside, which is 2. Half of 2 cancels, and we have the 2x minus 1 to the 1/2, which is square root of 2x minus 1. Everything is correct, so we would make sure we put the plus c on it since it's the indefinite integral, and there we go. But how do we do this using the change of variable method? Now, like I said, change of variable method is a lot like U-substitution, where we have to identify an expression that we're going to call u, and what we want that to be is really the inside part. So this 2x minus 1. Then we would identify what du is. So the differential of u, or the differential of 2x minus 1, is just 2 dx. Now, we're going to go back and substitute some things back into this integral. For instance, we're not going to take the square root of 2x minus 1, we're going to take the square root of u. And we're also going to have to substitute for this dx. Now, I know that du is 2 times dx, so that would mean that dx is 1/2 of du. So that's what I'm going to substitute for dx, is the 1/2 du. Now, one of the nice properties about integrals is that if I'm trying to take the integral of a constant times a function, that's the same as the constant times the integral of that square root of u, du. So we're going to take that integral, and the integral of u to the 1/2 is going to be raise that power by 1 to 3/2, and then take that coefficient that's on front, 1, and divide it by 3/2, so 2/3. Then when we simplify, the 1/2 and the 2 will cancel, and we have 1/3 u to the 3/2 plus c. And we finish it off by writing our answer in terms of x. Right now we have it in terms of u. We integrate it in terms of u, but we need to return our answer in terms of x. So we'll have 1/3 times whatever u was to the 3/2 plus c, and u was that 2x minus 1. All right, so then we have another method for something that's a little bit more systematic, kind of feels more concrete than just guessing and checking it out. This is called the change of variable method. Let's try another one. This one looks almost exactly the same as the last one, except we're going to take that square root and multiply it by x. The idea is still the same, that we want to call that inside part the u. So this 2x minus 1, that's what I'm going to have be u. Which would mean, again, du is 2 dx. Now, when we start to substitute all of this stuff in there, I have this 2x minus 1 that I can substitute under the square root. That's not a problem. And just like before, we saw that dx is going to be 1/2 of du. So I'll have 1/2 du here. But what about that x? And we need to go back to how we defined u to be 2x minus 1. We can rearrange this to determine that x is going to be u plus 1 all divided by 2. And that's what I have to substitute for that x right here. U plus 1 all over 2. Now this looks like a mess, and it actually looks like it's worse and harder to integrate than the original function was, or the original integral was, but it's actually not. When we simplify what's going on here, I'm dividing this by 2, so that's the same as multiplying by half, and that half times the other half would be 1/4. We'd have u plus 1, and square root of u is u to the 1/2. Like before, we said we could take that 1/2 and pull, or 1/4, and pull it out of the integral. And I can also distribute that u to the 1/2 inside. So we'll have u to the 3/2 plus u to the 1/2 du. Now, this is actually just goes back to that power rule again. And we integrate along the way. So increase the power by 1, so 5/2, and divide by the power, 2/5. For the next one, u to the 1/2, increase the power by 1, so 3/2, and divide by that power, 2/3. We can distribute that 1/4 inside, and we will get 1/10 u to the 5/2, and 1/6 u to the 3/2, plus c, of course. And our last step is to put it all in terms of x. Right now we have all these u's in there. We're going to take those u's out and put in 2x minus 1. So we'll have our final answer of 1/10 times 2x minus 1 to the 5/2 plus a 1/6 times 2x minus 1 to the 3/2 plus c. So before we get too far along, just kind of pause and think about the steps of how we're going to use the change of variable method. The first thing is we have to identify what u is. This is a U-Substitution process, so u is going to be the inside of the integrand. All right, so when we think about a chain rule, the inside function is what we're going to want to be u. Next, we identify the x, dx, and du as needed. And we're going to substitute those to have an integral written in terms of u. After that, we just integrate like normal. And when we're done integrating, we'll have an expression that's written in terms of u. We need to get that answer back so that we can have everything written in terms of x. So here's one that's big and ugly and very intimidating. But we're going to use the change of variable method, this U-substitution, to help us out. First of all, when we identify what u is, there's a lot of stuff that's going on We have a fraction with numerators and denominators. They're different. But in that denominator, I see this thing being raised to the second power. So it looks like that 1 minus 2x squared, that would be the inside function. So that's what I'm going to let my u be, is that 1 minus 2x squared. Next, we're going to have to identify what the differential is, so what du is. And the differential of 1 minus 2x squared is going to be negative 4x dx, which is super helpful for us because we have that negative 4x in the numerator and our dx on the outside, so we don't really need to do any other rearranging. We're able to just start substituting right now. Because we have that 1 minus 2x squared is our u, so the denominator is going to be u squared. That 4x, or the negative 4x dx, turns into our du. And so we'll leave our numerator of 1. That means that we're taking the integral of u to the negative 2 du. Again, just another power rule situation. So we increase the power by 1 and divide by that negative 1. Replace everything to write it in terms of x, which is going to mean taking the u out and replacing it with 1 minus 2x squared. You can leave your answer like that. Of course, if you prefer to write it as a fraction, you can. How about one last example? This one looks even crazier because of all the trig functions that are happening. I got a sine squared of 3x times cosine of 3x. So it looks like I got a function inside of a function inside of a function and times another function. So a lot of things to keep track of. So let's think of the one that's kind of the more complicated one. If we have, since we're multiplying two trig functions together, that sine squared and that cosine, I'm going to look at the sine squared one. Because I have a trig function that's being squared, I'm going to let u be the trig part, the sine of 3x. Then, when we take the differential of that, the differential of sine is cosine. But I also have to multiply by the derivative of what's inside, because we have a chain rule situation. So cosine of 3x times the derivative of 3x, which is 3, and then finish it up with dx. Okay. When we go back to substituting everything into the integral, we have some things all set up. For instance, that sine of 3x, that's right here. So u squared. Then we have cosine of 3x, which is really, really close to what our differential is. To find out what cosine of 3x dx is, we just have to divide by 3, so 1/3 of du. Now, just like before, with that 1/3, we can pull that out in front, and then go 1/3 the integral of u squared du. And this is a much easier function to try and integrate. But the integral of u squared, we increase the power by 1 and then divide by that power. So our answer is going to be 1/9 u to the third plus c. And then we can finish it off by writing it in terms of x by taking the u out and replacing sine of 3x back. Of course, we can clean that up a little bit. If we want to call it sine to the third of 3x divided by 9, you could do that too if you wanted. But that's how you use the change of variable method.